Okay, Unit 5. Unit 5 is all about polynomials, and if you may recall, we start this off with the exploration of this function right here, f of x equals x to the n. That's called a power function, and we started off by trying to understand how that thing behaves based on different values of n. So before jumping into a couple of these problems, I thought a quick little review might be if we go back to Desmos here. And this is something we looked at in class. And if you take a look at what's going on here, we have a graph right now of, this is the g of x here. G of x equals x to the m and m equals 2. So right now we're looking at the power function when its exponent is 2. That's just y equals x squared, and that's why it looks like a parabola. Notice how there's some key points on this graph here. I have negative 1 and 1, 1 and 1, and we're going to just make sure to keep your eye on those as we take a look at what happens. So as we explore what happens with different even values of n, if I move this up to m equals 4, this would be y equals x to the 4th. You can see that it kind of squares out and grows more quickly, which makes sense because raising something to the 4th power means you're multiplying it more quickly. But notice how those two reference points I mentioned, negative 1 and 1, 1 and 1, don't change. One of the problems talks about those. We'll take a look. But you can just see what happens. If I slide this back and forth, when m is 16, you can see this gets more boxy and grows more quickly. So that's the first thing to notice. Notice the end behavior, though, here as well. For all these evens, the graph is heading up, it's positive up and down. Sorry. Got distracted there. It's heading to positive infinity both when things go left and right. Now if I turn that graph off and take a look at the odds, put on h here, we can see what happens. Now we have the disco function kind of look. And if I actually make the exponent equal to 3, so right now we're looking at y equals x to the 3rd power. You get our standard disco function, and again the end behavior of that is that one side heads up to infinity, the positive x side, and then as x goes towards negative infinity it heads down. And you can see that same basic style happens as long as I leave the exponent odd, but again it gets more boxy and grows more quickly as I make the exponent higher and higher. And notice how there's that 1, 1 still shows up on the graph, but now instead of negative 1, 1, this point down here, negative 1, stays on all these different graphs. And it's something to think about why that's happening. If I turn this one off and go up to the top, this is just a generic f of x equals x to the n. When x to the 1 is just a line, that's why we see that line. But now as I move this up, you can see both arms raise up. It's because it's an even power. Then it goes down to a disco when it's n equals 3. Then it pops back up, disco, goes back and forth. So the takeaway here is that that exponent tells you everything you need to know about the shape. If it's even, it has the look of x squared. If it's odd, it has the look of a disco function. And then the higher the number, the more boxy and square the curves are, and the more quickly it grows. So with that in mind, I think we're now easily equipped to answer question 1 here. Question 1 says basically for 4 different values of the exponent, let's identify the graph here. Sorry. Okay, so well, the first thing to note is that we have 2 evens and we have 2 odds. So 2 and 10 are even, 5 and 15 are odd. And so let's take a look at the end behavior. Well, we know this one here has to be even because the arms go up. And this one also has to be even since the arms go up. This one has to be odd. This one has to be odd. Now let's take a look at kind of how the curves look here. Here we see this one's more rounded. This one's more square. So this one here has to be the smaller number. So we know that this one has to be n equals 2. And then the other odd here is n equals 10. And then for the other two, we can do the same thing. This one here versus here. Well, this one is more rounded. This one is more flat and square. So this one has to be the higher odd number, which is 15. And this one will be the lower odd number, which is 5. So this one is asking about those couple of those reference points I was talking about. It's like, why are these 2 points always on that graph? Well, this is just a matter of simply plugging in these 2 input values, 0 and 1. So just plug in 0 and see what happens. If we put in 0 into this equation, into this function, we get f of 0, which is simply, which is x, so we're putting 0 in for x here, which is 0. Well, 0 times itself as many times as you want will always equal 0. So we know that the input of 0 creates an output of 0 no matter what that is. So that's why that point's always on the graph. And now we do the same thing here. Plug in 1 into the function. So f of 1 to the n. So here we're going to take that 1 and stick it into our function definition, 1 to the n. Same thing here. If I take 1 and multiply it by itself as many times as I want, I'm going to always get 1. And so therefore 1, 1 appears on all these graphs no matter what n is. Hopefully you got the gist of this by now. This is describe the end behavior of the following functions. I'm just going to do this graphically. Now all we have to know is we have to look at this exponent, and that's going to tell us, and look at whether it's even versus odd and whether it's high versus low number. Actually, we don't even need that for the end behavior. We just need even versus odd. So the odds are going to look like disco functions. So the end behavior of A and C are going to essentially look like that. The graphs are going to disco out on us if we graphed them. And then this one's an even function. So that end behavior is going to look like this. And if we actually sketched the graph, it would look something, well, it's pretty boxy actually. It would look something like that. But again, the end behavior is about what these arrows are doing here. That's what that's what it means by end behavior, is what's happening as x gets really big or really small, or really negative, really positive or really negative. So you're just describing which direction these arrows are going. Are they heading up and to the right or down and to the left? Okay, for 4 here, I've just started off with a quick sketch of what this power function looks like for even and odd. Remember what the range is? That's the potential output values. So when we're doing that, we're trying to scan in this dimension this way. So we're going to take a look at what's going on as we look at the graph this way, from the left. And if we look at the possible output values here, we see that all the values here are positive only, or not negative. Positive plus 0. There's nothing down in this range, so the outputs here can be between 0 and infinity if x is even. But here, if we look and scan this way, we see that every possible number can come in the output range here. So all real numbers, all reals. And so we're going to just write the range of this guy as negative infinity to infinity. And so that we can see that the range of outputs depends on whether n is odd or even. And this makes sense because when n is even, even when we have negative inputs, we're squaring them or something like squaring. So you're multiplying a negative number an even number of times, which turns them positive, which is why you can never get negative numbers down here in the outputs when you have an even graph, an uneven exponent on the graph. Okay, this is the last of the questions on the power functions. Here we have the graph of f of x equals x to the 6th, x to the 10th. Hopefully you can sleuth out which one's going to be seen below here. We know for sure that they're both even because the end behavior is heading up to the top. And then we just got to figure out which one looks more boxy. Well, it certainly looks like that blue one is more boxy, so that blue is going to be x to the 10th, and that dotted red one is going to be x to the 6th. So now the question is, why does the solid graph lie below the line here? So like when we look at the outputs, why is this one underneath? Why is the blue one underneath the red one? Well, we can just take a representative value, and it's only below there between 0 and 1. You can see that it crosses and goes the other way. And the same logic will explain why. But if we take an input that's between 0 and 1, so I'm just going to pick a random number, say like 0.5, and see what happens. If I take 0.5 raised to the 6th power, which is what that would mean. That means, and this should feel a little bit familiar from our exponential unit. That means take the number 0.5 and multiply it by itself 6 times. So 0.5 times 0.5 times 0.5. Well, you know I'm shrinking every time I multiply by a 0.5. And so if you actually put this on a calculator, you'll get 0.015625, which is that number. Now, if instead I take something and multiply it by 0.5 10 times, that means I'm shrinking it even more. So you're shrinking it by multiplying it down by another 0.5 each time. If you put that in a calculator, you get 0.00097. This number is smaller than that number, and so that's why if your output is smaller, you lie below. And this will be true as long as that input value is between 0 and 1. And you'd see that the opposite happens when it's greater than 1, because when you multiply by something greater than 1, it makes it bigger, and then for that reason, that's why the blue line is above the dotted red once you get past 1.